Revision, we're there, we've made it. It was a long and torturous journey, but we've made it. It wasn't. It was an enjoyable journey, and you've learnt a lot, and I'm taking this off lecture mode. Oh, this is horrible. Full lighting. Take these spotlights off me. That's better. So, we're near the end. We'll be covering revision today and probably half of Wednesday's lecture, and then I also emailed, I will then go over test solutions in the second half of the Wednesday lecture. I think there'll be time then. Monday, Tuesday people will be getting their tests back, while Monday people will have already got their tests back. On Wednesday, I will bring the remaining test papers to the lecture, and you can pull your paper out if you come to the lecture. So when I talk about it, you have your paper in front of you. Then the remaining test papers will be returned in the practice class. If you don't pick them up, then the leftovers will be put in the office for you to collect from there if you wish. Solutions will not be posted. Okay, what have we learnt? What have we learnt? We have learnt so much, it's amazing. It truly, truly is. But what we've learned is only a very small part of the whole civil engineering thing. So if you don't like what you've been learning in the last semester, I was only talking about structural engineering. Okay? So from engineering, doing this subject, we were in civil. But within civil, we have all these different sub-branches. And we were only looking at, we were only looking at buildings per se, structures. We didn't look at anything to do with transport, water, environmental, geotechnical. And then within structural engineering, we again limited ourselves just to structural analysis, which is of course the most important part, while a crucial part. But you can see we actually brought ourselves down and just focused on a very small component of engineering in general. So what is structural analysis again? Just reviewing. It allows engineers to design before building an efficient, economical and functional end product. If you had to build a shed, you could knock something up, okay? Whether it would be the most cost-effective or the most structurally sound shed would be under question, but something could be built. So what engineers do before starting the building process, we design. So we come up with an energy efficient, materials efficient, most structurally stable structure we can. Okay? Now, in terms of structural analysis, there are two components, the qualitative understanding and the quantitative process. And once again, we really focused on the quantitative process. I explained to you how we use mathematical models to predict stresses and movements. So I taught you theory. Theory tries to model as closely as possible reality, but when the two differ, okay, it could be your model is wrong, it could be your model is poor for your particular situation. But in general, the modelling we use, the methods we used are very accurate for simple beams, okay? So what I explained to you is actually very accurate and very simple way to analyse beam structures. When you get more complex structures, when you get three-dimensional tanks and silos and round buildings with forces in all directions, then you may go to more complex analysis. But for the majority of your rectangular type structures with beams, okay, what I've taught you is accurate, is pretty accurate and quite simple, as you've learnt. So all these tools we've learnt, well, let's go through again. These are all things that if I mentioned them 12 weeks ago, you would have gone, I have no idea what she's talking about. So I do want you to pat yourself on the back to realise that you've learnt a lot and you understand a lot. So we started off with load paths. Okay, we now know we need to follow the way loads work through a structure. A common question I'm getting now with Project 3 is, Lizzie, do I put the roof loading on the secondary beam? And I'm saying to you, you work through the load path, you tell me whether the roof load is acting on the secondary beam. So this is not a high-tech question, this is a logical, let me follow the loads through to the support. If the load is not passing through that part of the structure, it should not be loading that part of the structure. So you know we have to follow load paths from their starting point down to the ground to see where the loads transfer to. And we know we have different structural forms. We have loads can be transferred through beams, they can be transferred through truss structures, they can be transferred through arch structures or through some sort of cable structure. So the loads, whatever they are, will transfer through that structure. How they transfer through that structure is a function of the structural form, whether it's bending, shear, axial compression, axial tension, is a function of the structural form. So we focused on trusses and beams because trusses and beams are the most two common structural forms. We don't use arches so often, and we don't use cables very often. So the first thing when we looked at our structural forms was we had to ask ourselves, well, what are the forces acting? So we then looked at load types and load case classes. Then we used equilibrium to solve for the reactions. We checked whether our structure was stable. Then when we looked at trusses, we actually used the method of joint sections. Once we had the internal forces, we were able to then design those members to see they weren't overstressed and whether they buckled. And then we moved into beams as our section structural forms. We learnt about shear force diagrams, bending moment diagrams. We learnt how to check deflections. And finally, this week in the practice classes, you're looking at indeterminate structures. So what I'll do in this revision section now, I will go through each topic in turn and then try and pull out an past exam question for you so you understand what the exam type of questions you'll get asked in the exam. So all past exam papers are on Moodle. We provide answers, not full solutions. There are 2 papers there with full solutions if you want to actually see the form the solutions take, but we do not provide our solutions to all questions. When you do look at past exam papers, you'll see the questions are actually asked in order of the material taught. I would love to actually muddle up the questions, the order of the questions, but if I did so, I'm sure I'd get an even higher failure rate than I currently get. So have a look so you're familiar with the exam questions. The first topic always relates to dead live loading. The second topic is usually axial compression buckling. Then we have truss question. Then we have a beam question. Then we have a bending stress question. Then we have a deflection checks question. And finally, an indeterminate question. So get yourself familiar so you're comfortable with the format of the exam paper. So let's now work our way from the beginning. These mathematical models we learnt about are theoretical models. So when we look at reality, we then have to say, how do we apply that loading? And we learnt that we either apply the loading as a UDL load, as a point load, or as a moment. Now, this UDL load can, of course, have other forms. It can be some sort of linear varying load. And we did a little bit on that. But primarily, we limited ourselves to a uniformly distributed load, a load of units kilonewton per metre, or a point load, or an applied moment. So these are our theoretical loads. So you can look at a structure and say, if you have a long beam and you have this pile of dirt in the middle here, soil, you can go, well, that's not quite a point load. But if it's actually only taking up acting on a small length of the beam, you would then say, okay, well, let's assume a theoretical point load is acting. So we have to model what's there as best we can and as most conservatively as we can. So as well as coming up with a theoretical model for the loading types, we then had to come up with a model for the support types. And we came up with fixed, pinned, roller. a roller only providing restraint in one direction here, a pin in two directions, and a fixed support, a moment restraint as well. So with a pin support and a roller support, a pin and roller support, with load on, the beam deflects down and you have rotation at the support. However, if you have a fixed support here and you put some sort of load on, there is no rotation at the fixed support. So this reaction, this support provides rotational restraint. So when we ask you for the reactions, we're not only asking you for force reactions, we're asking you for moment reactions as well. And you have to go, that's a fixed support, there's a moment reaction, pin support, only force reactions. Then we moved on and looked at the classes of loading. So when we look at loading, we go, okay, well, there's wind load, and then there's snow load, and then there's people load, and then there's dead load. So we divided up our loading into dead loading, live loading, wind, earthquake, earth pressure, liquid, and we just limited ourselves to dead and live loading. Dead loading being self-weight or permanent fixtures, such as the chairs in this room. They are bolted in, so they are considered permanent loading, so dead loading. You are live loading, you are transient, can move in and out. If the chairs were not fixed, if they were just tables and chairs, such as up here, the chairs here, the furniture would be considered live loading because it can be moved around. Then we have to turn this real life loading into, we have to give values to it. So we learned how to turn dead loading and live loading into a uniformly distributed load, or if we were talking about a slab, into a load kilonewton per metre squared. So our plan area, over our plan area, or a live load. So we know to calculate dead load in general, if we wanted in terms of kilonewton per metre, we would effectively just work out how much our dead load is in kilonewton by multiplying our volume times our density. And then we want to turn that into a load kilonewton per metre. We know we would just divide that by the length. And I showed you, in terms of volume, we can write volume as area times length times density, and then we divide by length. So thus, when we're dealing with dead load, we only really need to look at the cross-sectional area times the density, and that is because you can see our lengths cancel out. So you can do it the long way or the short way. You do it whatever way you get it right. Don't take shortcuts and get things wrong. Don't mind how you do it, whether you go, it's easiest if I calculate the total load. Whatever you find easiest, you do it that way. So in terms of the live load as well, in the end we came up with an equation where we say, well, the live load in terms of kilonewton per metre is whatever the live load is, and when we're given a live load, we're always given it in terms of kilonewton per metre squared, how much live load acts on an area. So once again here, if you then want to work out that live load in terms of kilonewton, you would then say, well, that's my live load times my area, B times L in this case, and then when I want it in kilonewton per metre, I divide by the length. And you can see here, once again, your lengths cancel out. So the long way, not much longer, one extra line. The short way. However you understand it, you do that way. In terms of slabs, we usually don't look in 3D on the exam paper, but again, if you want to know how much a slab weighs in kilonewton per metre squared, you just get density and you multiply by thickness. And that's because what you would do is you would get your density and multiply it by volume and then divide it by the area. So again, everything cancels out except your thickness. So we got these loads, and these loads were real life loading. These were the loads that actually occurred. And it's not enough that we design our structures for the real-life average loads, because if those loads, for whatever reason, are bigger, then our structure will fall down. So we never design for average loads, we design for extreme loads. And what we do is we define our loads as being characteristic loads and loads that have a 5% chance of being exceeded. So all the loads you're given are not average loads. They are loads up here, and a 5% chance of being exceeded means 95% of values lie below that load. So when we say the live load is, calculate the dead load, assume they are characteristic loads. They are these loads up here. So we design for extreme conditions by putting extreme loadings on. Now, characteristic load isn't that extreme. It's just a load that has a 5% chance of being exceeded. So that is still a 1 in 20 chance of being over-exceeded. So 1 in 20 doesn't give us good enough odds. So if I say the structure has a 1 in 20 chance of the load being exceeded, therefore a 1 in 20 chance of the failure of the structure failing, you would go, too risky. Well, it's too risky if you're talking about people's lives, people being injured by your structure failing. So what do? You've learnt how we add load factors. We multiply our loads by load factors. And we then call our design limit state design. And effectively what that limit means is we design up to the limit, the limiting yield stress, or the limiting stress. So we then take the loads up, the stresses up as high as they possibly can be. But what we've done is we have increased our loads by our load factors. So instead of saying, let's put the dead load on and design for strength, we put the dead load on plus 20% extra. Instead of saying, let's design for this live load, we go, no, let's put the live load on and an extra 50%. So we put bigger loads on, and then we design right up to the yield stress. So some people say, oh, my structure's being stressed up to 245. Oh, that's too close to 250. Let's put a bigger section in. No, you're allowed to stress it up to 249.9999. And then you don't go, oh, that's too close, that's about to fail, because your factor of safety is in your loading. You've put extra load on. So we call this limit stress design, and that's to compare it to permissible stress design. In permissible stress design, you actually put the true load on, and then you don't load it up to yield. You load it up to maybe 70% yield. So for strength, we increase our loads dramatically. For deflection, we actually reduce them. And that's because if something deflects too much, there isn't a risk there of someone being injured. There's only really a risk there of maybe a crack appearing. Okay? So when we design for strength, when we design for deflection, for serviceability, we then put equal weighting on the design. You then don't go, oh, serviceability isn't as important, it doesn't matter. You have to ensure that both criteria are met. And the fact that deflection maybe isn't as crucial and important is there because you have put smaller load factors on. Okay, let's do an exam paper. Question? Have a read. We have a 20 millimetre thick plate. It's 8 by 6 metres as shown. It's used to support a concrete slab in the middle, 250 mil thick. It's not as wide, it's only 3 metres wide. And on that whole area we have a live load of 6 kilonewton metre squared. The steel plate is supported by 2 equally loaded I-beams as shown. And you're given the weight of the I-beams. So they weigh 24 kilograms per metre. Question very simply, calculate the ultimate limit state design load on each steel beam by applying the appropriate factors of 1.2, 1.5. This is quite an old question. Not sure we always tell you what the appropriate load factors are. We would say calculate the ultimate limit state load and assume you know the load factors are 1.2, 1.5. So be clear what ultimate limit state load you're being asked for, whether it's ultimate or serviceability. So what limit state load you're being asked for, whether it's the strength one or the deflection one. So we're given the density of concrete and the density of steel. And as I said way back in lecture 1, you can come to me and say units of density, Lizzie, are not kilonewton per metre cubed. No, we're engineers here. We're lazy when we come to our terminology. Look at the units and be clear what units your values are in. Okay, so for a question like this, I'll then just move across. We'll look at calculating the dead load first. Now you are asked, if you go back, the ultimate limit state design load in kilonewton per metre on each beam. So we're only looking at the load on one beam. So first thing I write, okay, my dead load kilonewton per metre on one beam. And I write that out so I'm clear in my own mind what it is I'm doing. That comprises the beam self-weight plus the steel plate plus the concrete in the middle. So I have 3 components of that. So let's look at our, well, we know what our beam self-weight is. If you go back to the question here, we are told the beam weighs 24 kilograms per metre. So that weighs 24 kilograms per metre, but we want to calculate it in kilonewton per metre. So we know we multiply that by 10 to convert it to newtons, and then we divide it by 1,000 to bring it back to kilonewtons. So that comes to 0.24 kilonewton per metre. There's always a certain percentage of people that always forget to change their units. So make sure you're not one of those people. Then we have our steel plate. So I want it in kilonewton per metre, and I know I want it on one beam. So I'll do it 2 ways, the long way and the short way. The long way, I would just work out the total volume. 6 by 8 by it's 20 mil thick, 0.02. There's my volume. I multiply that by my density. If you go back, we're told density of steel. It was given up to us in kilograms per metre cubed to confuse us. Remember, we don't bother with 9.81. We round it up to 10. So that works out to be 78.5 kilonewtons per metre cubed. So we would multiply that by 78.5. Now currently, this number here has units of kilonewton. We want it in kilonewton, and that is the weight of the total steel plate. So we want it on one beam. So I'm going to say divided by 2 beams. And then I'm going to divide it by the length, 8 metres. And that then gives me a value of 4.7 kilonewton per metre. Now, that's what I call the long way, and that word long is not an insult. When I do it the quick way, I'm going to say, okay, so my quick way is based on saying that it's cross-sectional area times density. The cross-sectional area here I've shown in yellow. Cross-sectional area on one beam is 3 metres wide by 20 mil thick times my density of 78.5, and that, when you multiply it out, also gives you 4.71 kilonewton per metre. So that is an alternative method to the long way. So I've got my beam self-weight, my steel plate, And now I've got the weight of the concrete. So I want that also in kilonewton per metre on one beam. So I'll do this way, the quick way only. Okay, so if I go to highlighter, but I want to change my colour because I can. So the cross-sectional area here on one beam is that area in green there. Excuse where I've gone outside the line. So that cross-sectional area there is 1.5 metres wide by, it's 250 millimetres thick, times the density of concrete, which we were given back here as 24 kilonewton per metre cubed. And if you look at your units here, I've got metres times kilonewton per metre cubed. So just by looking at your units, you can say, yes, I have the right units of kilonewton per metre. So I have my 3 dead load components, and thus my total dead load, oops, let me get an extra page in there. So my total dead load now in kilonewton per metre on one beam will equal my 4.71 from my steel plate plus my 9 from my concrete plus my beam self-weight, which is a load of 13.95 kilonewton per metre. So there's my dead load complete, and now we need to look at live load. So when it comes to live load, we also want that in kilonewton per metre on one beam. So I'll again do this the long way and the short way. Our total live load, our live load is 6 kilonewton per metre cubed. So it's 6 kilonewton per metre, squared, because it's acting on the area. And I can multiply that by my total area, 6 times 8. So that's metre squared. So if you look at the units there, currently that's a total live load of 6. But I want it on one beam, so I divide by 2 beams, and I want it in kilonewtons per metre, so I divide by the length of 8 metres, and that gives me a load of 18 kilonewtons per metre. Alternatively, I could have said, well, it's equal to my live load of 6 kilonewton per metre cubed times the width. And the width on which it acts of one beam is 6 times 3, which is 18 kilonewtons per metre. So can you see? Same thing. However you want to do it, doesn't matter. You're not going to get more or less marks if you get the same answer. Sorry? No, because this is, that should be, yes, thank you. 6 kilonewtons per metre squared there, yeah. So I've got a kilonewton per metre squared, and I'm multiplying it by a width of metres. And I've only multiplied it by 3 metres because I'm looking at the load on one beam, and the width of the load acting on one beam is 3 metres. So finally, our ultimate limit state load, once again on one beam, in kilonewton per metres, is equal to my dead load factor times 1.2 plus my live load factor times my live load. So 1.2, 13.95 plus 1.5 times 18 gives you a load of 43.74 kilonewton per metre. So as long as you don't panic and you work through the calculations logically, you should be fine. sometimes we put, okay, look at the exam, flick through it when you first get it and go, okay, there might be what Lizzie calls a scare question in there. It's a question that when you initially look at it looks pretty scary, but they're just trying to trick us, to scare us, and we can do it. So here is the scare question on the 2012 paper. So people looked at that and went, oh my God. Now, this question can actually be done in 4 lines. It's not hard. You just have to breathe deeply and not panic and tell yourself anything on the question, on the paper you can do. So have a read. We have a concrete slab, 200 mil thick, 5 metres by 10 metres long, supported by 2 equally loaded, simply supported concrete beams. Also 10 metres long. The concrete slab supports a concrete ramp with triangular cross-section. That's the scary bit. 3 metres high, 4 metres wide. Each of the 2 concrete beams has a cross-sectional dimension, 400 by 200. Okay, this would get scary. Quite often when we give you a beam cross-section, we give it to you as a hollow section. And that's because people are not capable under stress conditions of subtracting the inner area from the outer area. Okay? So when we ask you for a question like this, get that right, subtract, you would say it's the outer area, take away the inner area. People only take away 1 thickness. You know, when you're given the thickness of the plate here, they forget to take away 2 thicknesses. So if you're faced with a question like that, ensure you're working with the right dimensions. This question is solid, so that part of it's easy. Only dead load is considered, so they're not even asking you about the live load here. So all you have to do is determine the values of the ultimate limit state loads W1 and W2 on each beam. So ultimate limit state, all you have to remember to do, because it's dead load, is use your load factor of 1.2. So you just have to calculate those 2 loads. So let's give W1 a go. W1 is the easier one. You forget about the cheese bit. These little holes make it look like cheese, don't they? I look at that question. I didn't write that one, and I think cheese. Okay, so W1. So for W1, what's our dead load? Our dead load is equal to our slab plus our beams. So, are you happy I do it the quick way with the cross-sectional area? So, for this question here, highlighter, I'm going to base the slab weight on that cross-sectional area and the beam based on that cross-sectional area. So, my slab load is equal to area times density. The cross-sectional area I'm talking about, the whole thing here, is 5 metres wide. So that length in there is 2.5 metres. So it's simply 2.5 times 0.2 times the density of 25. And that gives us a load of 12.5 kilonewton per metre. Our concrete beam itself, well again it's just area times density. The area of our beam, 0.2 times 0.4 times 25. That gives us a value of 2 kilonewton per metre. So what is W1 equal to? It is just 1.2 times 2 plus 12.5. And that gives you a value of 17.4. So if you are panicked and you go, I don't know what to do with the piece of cheese, forget about the piece of cheese, do the other half of the question, tell yourself I've done half the question, so I'm going to get half the marks. Okay? If there's a hard bit, quite often we have a part A, B, C. We expect everyone to be able to do the A, or just A and B. The part B will be more complex, okay? The part B may be to distinguish high distinctions from the rest. Okay, we've done the W1. Is everyone happy with W1? Okay, let's look at W2. I'm going to get an extra page in. I'm trying to be neat, or at least spread out. So let's look at W2 now. Now W2, oh my God, what do I do? It looks confusing. There are different ways to tackle this problem. W2 varies from W2 at the high end to W1 at the low end. So what we can do is, so we don't get confused about the fact that it's reducing in load, let's just assume it's uniform. There are different ways to tackle this. I would just assume I have a uniform load of value W2, and then based on that assumption I just calculate the greatest value, and that's the value of W2. So thus I'm going to assume in the centre, and there are different ways to tackle this. 4 metres, the concrete is 3 metres deep. So thus when I work out now the weight of the concrete, and I base it on cross-sectional area, and so I now base it on cross-sectional area. I'm looking at that cross-sectional area plus my W1 value. So how about I take it all the way down here? So when I'm saying it's assuming it's 3 metres deep, it's not actually 3 metres deep. Can you see there? It's actually 3.2 metres deep throughout. So the weight of my concrete here, in terms of kilonewton per metre, is just 3.2 metres deep times 2.5 metres wide times the density of concrete. We said, what did we say our density of concrete was? 25. And I don't have a numeric value for that. Has anyone got a calculator? 200? Kilograms per, oh yeah, sorry. Now, no, that shouldn't be 200, should it? It is? That's 200 kilonewtons per metre. So therefore, what is W2 equal to? It's equal to my 200 plus the weight of the beam here, which we said was 2. That's the beam weight, and that's the, I call it the cheese weight. So that's the value. We then multiply that by 1.2. Now I've got messy, haven't I? Hang on. I'm trying my hardest. So W2 is equal to 1.2 times 200 by 2, and that is a value of 240. I can't read this writing there. What is it? 242.4. Excellent. Thank you. God, you guys are on the ball. Someone's working hard back there. Now, can you see how easy that was? Just don't panic. Now, question 1 now typically has a part A and a part B component. So in this question here, really, that first part here was relatively easy. It was just a dead load, W1, here W2. So that probably W2 would have been worth 50% of whatever that question was worth to calculate a W1 value and a W2 value. So not hard. Just don't panic. Now, question 1 typically does have an A and a B part. The B part is not hard. The B part now relates to a linear varying load. to ensure you can work out your resultant forces. So in the 2011 paper, semester 2, we had a wind loading on a cantilever beam that exerted a downwards loading that was not uniform. It had the distribution of 0.1x squared, where x, you can see here, is measured from A. So it increased in a parabolic fashion. Don't ask me why the shape's going that way and not that way, but you know what I'm talking about. Okay. A wire rope then was attached as well and exerted a further point load, and you were asked to determine the magnitude of the equivalent resultant point load on the beam and its location and direction from A. So a question like this, you would consider in 2 or 3 parts. Again, there's a point load on there. Oh my God, it's at an angle. Don't panic. Work through it bit by bit. So I would first say, okay, I'm going to work out the resultant force from my wind loading. So this resultant force we work out is equal to our varying load times dx. So we integrate it over our distance dx, and in this case it's between 0 and 9 metres. So we integrate our 0.1x squared. That gives us 0.1x cubed on 3 between 9 and 0. So that gives us a resulting point load of 24.3. Now, before we can proceed, we need to know where that resultant force occurs. So the location of the wind resultant from A is found by saying, well, x, this expression here, w, the integral of x, w, on effectively our resultant force of 24.3 will give us that distance. So that will give us that distance there. I'll call it x1. So we need to know what that force is before we even look at the point load. So where did I get these equations from? These are equations that are given to you on the exam. On the exam paper, that equation will actually be written by as the integral of x, w, dx, divided by the integral of w, dx. And we've done that integral of w dx, that's our total force. So we're saying force times distance is equal to our resultant force times its distance. Okay? Okay, so to find that resultant now, my term in the integral is now a cubic term because I've multiplied it by x, divided by my total force, and I'll leave you to do all that integration yourself. And in doing that, you say, well, that resultant force actually occurs at a distance 6.75 metres from x. So now at this point, I would draw a new diagram, and I would say on my diagram, I have my force of 24.3 kilonewton, and that is situated a distance 6.75 metres away. And then in a different colour, I would resolve this 15 into a horizontal and a vertical component. So this vertical component here is simply 15 cos 20 degrees, because you're told it's acting at an angle of 20 degrees with the vertical. And this horizontal component, hopefully it won't be a surprise to find out it is 15 sine 20. So a value of 5.13 kilonewton. So now we still keep the vertical component away from the horizontal component, and we say to ourselves, well, our total vertical force is equal to our 24.3 plus our 14 is equal to 38 kilonewtons. And where is it acting? Now we work out a new location for our total resultant force. So now we can say, okay, our total vertical force is this one here. This is our total vertical force, and now we need to know where that one's acting. So where does that one act? Well, again, you would say force times distance, your force of 14.09 times the distance of 4.5 where it was acting from A, plus your wind load times the distance that it was acting, 6.75 metres from A, and then you divide by your total load, and that would give you a distance of 5.9. So your final answer now, sorry, again, trying to keep this as neatly as possible. Oops, hang on, no, I want to delete all that. We know we have a resultant vertical force here. We've calculated the value as 38. And the distance it's acting. And then we have I meant to choose red. And then we have our horizontal force here component, which we calculated to have a value of 5.13. And then our final resultant here, using Pythagoras, would work out to be 38. And again, using trig, you can work out that angle in there is 7.61 degrees. So that would be as complicated as a Part B question would get. The easy ones would just give you that linear varying load and ask you to work out one resultant. In this case here, you had a linear varying and a point load, and the point load was at an angle. Okay, how quickly time flies. We'll continue this Wednesday, not tomorrow, Wednesday.